Hello, hello. Let's get the next session started. So in this session, we're going to have Michael Shtelma, lead specialist solution architect from Databricks, to give you a talk on scaling deep learning using data lake storage format on Databricks. Welcome.
Hi, everyone. Okay, today we will be talking about scaling deep learning pipelines on Databricks, and I'm going to show you how you can use Delta Lake tables for that, basically how you can feed the data from Delta Lake tables to PyTorch and use it for training. But at first we will see how the typical deep learning project looks like, how we can how like the typical deep learning lifecycle looks like, and after that we will make a step back and see how things get complicated if we are going to use the same data set for multiple projects, for multiple pipelines. And after that we will see what options we have now already available for that. So how we can use a shared data set for multiple training processes which might be running in the same time. And after that, I will introduce, to my mind, the best solution for that. It's DeltaTorch, and we will examine the DeltaTorch architecture. We will see a couple of examples, and then I will show you the demo, one of them, like the image recognition one, and another one will be working with natural language processing, actually with the Databricks Dolly. Okay. Here is the typical deep learning project lifecycle. As all other machine learning projects, it starts with the data ingestion. So we will have to ingest our data to the lakehouse, probably to the Delta Lake. And it's going to look like in the same way for different data types. In this talk, we will primarily use image recognition and natural language processing use cases, but it's going to work exactly in the same time also for sensor data and other types of data. Right. After that, we can do our pre-processing, and it might look like differently for different use cases. So for images, we maybe would like to pre-process them to do the basic conversion, convert them to the same format. Maybe remove images which are not that good. We can even build embeddings and then use embeddings during the training. For natural language processing, we can process our text data and like do the standard NLP task like filtering and so on. But after that, we get our data readily available for training. And in this talk, I will be talking about having the data stored as a Delta Lake table. So after we have our, after we get our data, we can train our model, we can evaluate it. Maybe we will iterate a couple of times until our metrics basically we get the metrics we want to get. And then we can do the deployment. But now let's make a step back and let's think how all that is going to look like if we have multiple teams which are simultaneously using the same data set for their training. So multiple teams might have completely different schedules. They can have different sprints. Some of them might have 2-week sprints, some other will have 1-week sprint. The models might take different time to train. And of course, the data will be delivered not always in the same time. So let's look deeper into that. So the biggest problem is that if if we are having data deliveries during the let's say our sprint, we can hardly compare our models, right? We can come up with the different model architectures. And usually we would like to compare those architectures to understand which one is better. But if our data changes in the meantime, we cannot actually use those metrics for comparison. Another challenge is if, for example, we are training a foundational language model, those training processes might be really long. can be like, I don't know, even a couple of weeks, right? And in that case, the data deliveries, the ETL pipeline might even affect the training process. So the summary is that we need a proper versioning to make sure that the writers do not affect our training processes, so the writers do not affect the readers. Usually for those use cases which we are discussing, the data sets can really easily become extremely big. So the size matters, and we have to be able to fast enough read the data and process, like do the pre-processing. I mean the last stage pre-processing which we do during training. For the image recognition use cases, usually we can do like simple image augmentation, we can like rotate images, we can do the random, like change different aspect ratio. But basically we can change a lot of different things, right? And we have to do it fast enough so that our GPUs still are utilized. So another point is that if multiple teams, multiple projects are using the same data set, they might not need all the data set in the same time. So usually they need to filter out some portion of it due to legal reasons or some other reasons, and they also don't need all the features, so all the columns. So here is another requirement. Basically, we need simple filtering, and we also have to do that without basically doing like the copy. Because of course, in both cases, we can copy the whole data set, we can just grab one version of our data, we can make a copy and use it for training. But that might be prohibitively expensive. And it also takes time, so that's basically the worst approach. Okay, so let's now summarize our requirements. So we need to be able to load data fast. We need basic filtering, we need versioning, and we don't want to copy the data. How can we do that? So what tools are available right now that can allow us to meet those requirements? We can easily store the data on a local hard drive. But in the cloud setting, that's going to be really slow because we will have to load them to copy them every time. Theoretically, it might work, but our GPUs would be kind of waiting for that. Of course, we can just load our data to cloud as the JPEG or PNG, and we can try to load those files directly while the training running. That might work, but it's quite hard to make it right. And if your images are really small, you will be still losing a lot on I/O, because that's going to be like a lot of cloud requests. And of course, we can utilize something like TF records, a special format. But for me, it looks like basically we are just doing a special copy for training. Because of that, I don't like this idea. So it just means that we have this additional copy, and we cannot use it for anything else. It's just for training. OK, there is another option. We can use big data formats. We can use Parquet, which is a columnar format. It's open. We can easily put all the data we have in Parquet, put it to cloud, and directly use for training. There is a basic support for Parquet loading in most of the frameworks. I think we have it for TensorFlow. We have it for PyTorch. And it's going to be fast. We have row groups and statistics, so we can easily filter out things we don't need. It's a columnar format, so we can easily load only the features we need. So everything looks nice, but still there are a couple of caveats. At first, Parquet doesn't support versioning out of the box. We also don't have transaction support. So what that means that if our pipeline, like our training, is running, and at the same time somebody tries to do the data delivery, like the ETL pipeline comes, there is no way to prevent that pipeline from affecting the training. So if the pipeline, for example, so the pipeline might even corrupt the data set, which can stop our training, and then we'll have to recover from the checkpoints. Another issue is if we are using distributed training, we will have to make sure that our ranks, like different processes, actually reading the same thing. It's not that easy. Basically, it's a nice approach, but in a case that we have writers that are writing data during the training process, it's really hard to get it right. So we can use Delta Lake, because Delta Lake is an open source storage format. It's a metadata layer over Parquet, so it has everything that Parquet has, but on top of that, we have transactions, we have performance, we also have support for versioning, and actually we have a lot more. So let's now discuss why actually Delta Lake can help us here. So Delta Lake has features like the ordering and data skipping, and that can help us with efficient filtering. So our ranks, like processes during the distributed training, will need to somehow understand what portion of data they need to load, and then we also said that we would like to have basic filtering. So with data skipping, we can reduce I/O significantly, and we can easily load our data. Another great feature of Delta Lake is that it supports batch and streaming in the same time, so we might have multiple data delivery like ETL pipelines which are ingesting our images or our text data, and those pipelines are not going to affect readers in any way. So basically that's like the biggest feature which makes it really good for training. And we have versioning, so we can easily fix the version. And for example, we can use version 1 during first sprint, and when we get more data, we can start using version 2 for the second sprint, or we can use just one version of the data for the whole project. Basically, that's already our, we can decide it in any way we want. But there is a small problem. There is no direct support for Data Lake in any framework. PyTorch doesn't support it out of the box. So we have to be a little bit, so we have to see how we can, what we can do about it. There is one tool which is called Petastorm. It's a really nice tool which is coming from Uber. Petastorm usually directly works with just simple Parquet datasets. But of course, we can use Petastorm, and we can use it, basically we can pre-calculate the list of Parquet files. We can calculate that list, and then we can directly send this list to Petastorm, and then Petastorm will load the data from those files. But there are a couple of caveats. So at first it's a workaround. We will have to basically write code for that, and we will have to maintain that. Another problem is it's not compliant with the Delta specification, because now Delta has a bunch of features. For example, deletion vectors, and we might get some other features in future, which will basically make this whole thing completely obsolete. And another issue with Petastorm is that it's quite slow. At first, it's like really memory hungry. It requires a lot of memory, and it does a lot of things, like it writes the data to cache, and at the end of the day, the whole training process with Petastorm can be quite slow. So the solution, I think, which is really simple and directly does what we would like it to do, is DeltaTorch. DeltaTorch is a new small library which allows us to use arbitrary delta table for training. It's compatible with PyTorch. It's basically just one function which allows you to create a PyTorch data loader and just to get your data in PyTorch. It also supports distributed training, so it automatically does the sharding, and it also supports partition filtering and versioning. So we like to use DeltaTorch. There are a couple of requirements. So our delta table, which we're going to use for training, must have an ID field. So just an identity column with auto-increment identity column, which we are using for sharding the data. But that's not that it's quite easy to calculate that using Spark. Okay, so here is an example. You can easily install Delta Torch using pip. From the Git repository, it's also available in the PyPy. As I mentioned, it's just one function, which is called create PyTorch data loader. And there are a bunch of parameters that you will need to specify. At first, you have to specify the path to our Delta table. After that, you'll have to specify the name of the ID field. And after that, in fields property, you can specify the list of your features. So you can have multiple field specifications. Those are our features, and they will be available during training. You can also specify a PyTorch transform for each feature. Or there is a way to transform the whole record as like with the function as a whole. We will use it during the NLP demo. I will show you that as well. You can, for example, for images, you can directly use Pillow to load the image. So all that is supported. You can also specify a number of workers. So that's important if you, for example, have a really heavy transforms. Then you might want to utilize your CPUs to transform the data fast so that your GPUs are not waiting for the data for the next batch. And you can set the batch size. So after that, you get your data load, and then you can just iterate it in a standard way. So as I mentioned, versioning was one of the important requirements. So with Delta Torch, we can specify the version of the Delta table. And we have discussed another requirement, which is filter. So we don't support arbitrary filtering, so you cannot use any field for filtering, but we support partition filtering. So basically, if you would like to filter out a portion of data during the table creation, you should use that field to create a partition using that field, and then we can easily specify the filter, which will just grab a couple of partitions. Why we are doing it in that way and why we cannot use any field? Because it's just like partitions are a metadata, right? So when we read the Delta table, we have all the partitions in the metadata, which is available, and we can easily filter out everything else without any additional requests. So it's a really fast operation. And because of that, it's implemented right now that way. We might in future implement some additional filters which will use not only partition columns but any other columns. Okay, so with Delta Torch, our pipeline, our deep learning pipeline, can look in the following way. So we have our source datasets on the left-hand side. We can have multiple ingestion pipelines. We can use batch pipelines. We can use streaming. We can use pretty much anything we want. And those pipelines are going to ingest data into our Delta Lake table. And on the right-hand side, we can have multiple training processes. We can have multiple models which are using the same data set, which are using the same table for training. And those processes can efficiently read from Delta Lake. They can use distributed training and all those things. Okay, now let's see how this whole thing is built internally. So Delta Torch is a really small library which is based on Delta Rust implementation. So that's a standalone implementation which heavily utilizes PyArrow. Basically what it does, it reads the Delta metadata and determines the list of the Parquet files and uses PyArrow to read the Parquet files. And after that, we can set the filters to PyArrow. We can do some basic calculations with PyArrow, which gives us really good freedom to do whatever we want after that. And we are using ID column to calculate shards. So as I mentioned before, we have ranks and we have workers. So we use this ID column to calculate what portion of data will be read by each worker process. So that's how it's going to look like with one GPU training. So we'll have our PyTorch data loader, and PyTorch data loader might run multiple workers. So on the slide you can see that we have 2 workers, and each worker might run multiple PyArrow threads. And we will have, each worker will have own shard of data. It will just add conditions to the PyArrow data set. So because of that, the data skipping and the ordering is really important if our data is ordered. And we have also statistics in Delta that helps Delta Lake to read only the data, like the Parquet files it really needs. In the case of a distributed training, we will have multiple GPUs. Each GPU will have own Python process. And so we will have one data loader for each GPU, like for each rank. And then it's going to have multiple workers. So in our case, we have 2 GPUs, 2 ranks, and each of them has 2 workers. So how it's going to work? At first, we will divide our data set in 2. So each rank will have half of it, and after that, each worker will get half of that half. Now, a small performance benchmark. I have run a really simple image recognition pipeline. Basically, I have trained, I believe it was ResNet, or maybe MobileNet, but I will show you during the demo which network was it. And on the ImageNet, I have used AWS, and I have used always 2 nodes of the G5 family. So I was using A10 GPUs. The node type, of course, was different because I'm using different types of GPUs. Different number of GPUs, as you see. And as you can see, that Delta Torch is almost 2 times faster than Petastorm. Okay, now is the demo time. So in this demo, I will just run it so that we don't lose time. So in this demo, I will be using PyTorch Lightning, and I will be using Caltech dataset. So Caltech dataset is not that big, but I have multiplied it. So actually, it's like the Caltech multiplied 10 times, just to make it a little bit bigger. And that's like a pretty standard PyTorch Lightning training pipeline. So at first we have to specify the path to our Delta tables. So we have 2 tables. We have one. Should I make it bigger? Is it too small? Okay. So we have 2 tables. One table is like our training data set, and another table is used for the testing. So that's, by the way, how the data looks like. We have our image column, which is binary, and we have the labels. And we have our IDs. And ID is just an identity column, so they really start at 1. You can run it. Okay, in the meantime, while it's running, we can take a look at the version. So as you see, this Delta table has a bunch of versions. We can easily grab the versions, and we will be using version 9, but we can, of course, specify any other versions. But for example, you can see that I have run the optimize command, so our version 9 is the optimized one, right? And okay, so here is our PyTorch Lightning data module. So at first we can specify our transform. So in this transform, at first we will convert our image to the RGB. We can also do the resize, and we can crop the center of the image. We can convert it to tensor, and then we can do the simple normalization. So those are quite standard PyTorch transforms, so we will use those. And here is a method which creates the data loader. So it's quite similar to the examples I have shown you during, in slides. So we are calling this create PyTorch data loader function, and we specify the path, ID field, two features that we need. We also specify here our transform, and we set the batch size, the version, and also we say that the shuffle is true. So Delta torches also support shuffling, so it's going to be done on the row group size. On the like actually it's even not a row group. It's like we're using PyArrow, and with PyArrow we read data using the record batches. So we will shuffle each record batch. Okay, and then we have our train loader. So basically we just call the same function a couple of times. Okay, so let's run it. And okay, now we have the main function where we are creating PyTorch Lightning trainer. And we have here a bunch of callbacks. I'm going to use distributed training. So for that, I'm going to use PyTorch, Spark PyTorch distributor. So here we can specify number of processes. So I'm using one node with 4 GPUs. So it's a local mode, and then we can run it in that way. So let's give it a couple of moments to run, and while it's running, I can show you the GPU utilization. So we can use NVI top for that. Oh, it's already running. Yeah, it's already running. So you can see we have 4 ranks, and looks quite good from the utilization perspective. Okay, so that concludes the first demo. And additionally, I would like also to show you how you can use Delta Torch with the natural language processing use cases. So you know that we have a Databricks Dolly, so that's the large language model which we have released a couple of months ago. I'm just going to use Dolly Pipeline just to highlight how you can use Delta Torch with something like foundational language models. So we are going to fine-tune PCR 3 billion on the Dolly dataset. I have, before that I have created, I have read the Dolly dataset and converted it to a Delta table. So I'm not going to show that. Basically, that's the standard Dolly notebook. Like at first, we are installing here a bunch of additional packages which are needed for the deep speed to operate. After that, we install the basic requirements. We're also using here deep speed for training. Okay, a bunch of simple widgets. And here is basically the main command. So we're going to run the trainer, and we will pass the model we would like to fine-tune, and we are going to pass also parameters that are pointing to our Delta tables with our Dolly dataset. And we have a couple of other standard things, including the batch size, output path on DBFS and locally, number of steps, and so on. So now let's look on the results. You can see now that we can load this model. That's a standard method that is part of the Dolly project. And after that, you can see that we can generate a couple of nice things. So we can write a love letter to Edgar Allan Poe. We can also generate a tweet that announces Dolly and a couple of other things. Now let's look inside the actual training. That's the that's the script that actually does the training, and deep speed runs the script for each GPU. So in our case, we have I'm not going to run it now, but as a test, I ran it today. It had 8 GPUs, 8 A10s, and we have a data collator. We also have methods, we have code which loads the tokenizer, we also load in the model from the Hugging Face, and after that we have the most important method for us. It's called preprocessed dataset. So here we are using the same function, create PyTorch data loader. So we are passing the dataset path, and we also have the same ID field. And here we have just one feature, which is called text. Okay. But here is a sorry. But here is a really important difference. We are not using here standard PyTorch transform. We are using like a custom transform, which can transform the whole record at a time, and it can also generate multiple features as a result. Let's look at this method. So why we need that? So in this particular method, so in this particular function, we are doing the tokenization. So we are using our tokenizer, and the tokenizer has two outputs which we are going to use during training. So we have our tokenized output, our input IDs, and we also have the attention mask. That's why we need this special function, because we cannot do that using a standard PyTorch transform, because from the standard PyTorch transform we cannot return two fields. And then we have a bunch of other things, and that here is the main train method. And basically that's where we are creating our data loader for the using Delta Torch, and we also can specify the data collator. So I can scroll up to show it. So here we also specify the collate function. So here we specify the collate function, so which is going to be applied for the whole batch. And so that's basically it. So here we have we are iterating over the epochs, and after that we are iterating over the data loader, and we are getting the batch from our data loader. We are transferring this batch to the PyTorch, and then calculating our logits, outputs, and doing the backward step. So here we are not using Hugging Face training, so we are doing the classical PyTorch training. So that concludes my demo. So what we have seen today, so I have shown you how you can use Delta Lake for training directly. So with Delta Torch, you can easily use your existing Delta tables for training, and you can use those Delta tables for multiple training processes at the same time. You can, in the same time, change your Delta table. You can ingest your data, and you can use it for training. So we're also looking for contributors. So feel free to contribute fixes, new features, or just come up with the feedback. Thanks, everybody. Now is the time for questions.